Right, so I'm here to tell you a story about a piece of work that I was involved with. And it makes an interesting story because it involves two completely different types of mathematics. So on the one hand, we have mathematical physics, which is the mathematics that's right on the border with physics. So normally you'd be doing calculations where the aim you had in mind was to model something that was going on in the world around you, or maybe to provide a theory for some experiments that physicists were doing in their laboratory. So it's a very practical, applicable type of mathematics. On the other side, we have number theory, which is a type of pure mathematics. And there are many interesting applications of pure mathematics too, but often what actually motivates the mathematician is not so much the applications, but the beauty of the mathematics itself. So the patterns and the structure of the mathematics is probably what drives the mathematician to study pure mathematics. So from the opposite ends of the mathematical spectrum, these come together in the piece of work that I'm going to talk about today. And so that's what makes it a sort of unusual story. Maybe a little bit remarkable. In fact, remarkable enough that it made it into a major Hollywood movie. So I'll tell you more about that at the end. So, but to start off with number theory, it is exactly what it says. It's the study of numbers. And so the numbers that we count with. And the building blocks of numbers are the prime numbers. So put your hand up if you know what a prime number is. Okay, so that's great. So, okay, someone define a prime number for me. Someone at the front so I can hear.
Indivisible by 1 itself.
Exactly. So it's a number that's only divisible by 1 and itself. It's a number greater than 1 that only has 1 and itself as positive factors. So, for example, 11 is a prime number because you can't write it as a product of two smaller factors. But 91 is not a prime number because you can write it as 7 times 13. So let's start writing a list of the primes. So what's the smallest prime number? I hear 2. So the smallest prime number is 2. So hands up if 3 is a prime number. Very good. Hands up if 4 is a prime number. So 4 is not a prime, right, because you can write it as 2 times 2. Hands up if 5 is a prime number. Okay, so 5. 6, is 6 a prime number? I'm getting head shakings. So in fact, we're not going to find any more even prime numbers because you can always write an even number as 2 times some other number, right? 2 times 2, 2 times 3, so forth. So we're not going to find any more even prime numbers other than 2. So 6 is not prime. 7 is prime. 8 is not prime because it's even. Hands up if 9 is prime. So it's not prime, because even though it's odd, you can write it as 3 times 3, right? So 9 is not a prime. 10 isn't a prime because it's even. 11 is a prime. 12 is even, so it's not a prime. Hands up, is 13 a prime? Yes, 13 is a prime. 14 is even. 15 is 3 times 5, so that's not a prime. 16 is even. 17 is a prime. 18 is even. 19 is a prime, and so forth. So here's a list of some of the first few prime numbers. So humankind has been studying prime numbers for an awfully long time. So for example, more than 2,000 years ago, Euclid knew that there were an infinite number of primes. So we could keep writing that list of primes, more and more and more, larger and larger primes, and we'd never come to the end of it, right? So we'd never find a largest prime. If you can think of it, some huge, huge prime, there'll still be many more primes that are larger than it is. So the list of primes goes on forever, and we can write them down as long as we want. We'd never get to the end of it. So you'd think that if people have been studying primes for all this huge amount of time, that we must know absolutely everything there is to know about primes. Right? Well, you might think that, but that's not in fact true. And so there are some things which are quite simple to describe about the prime numbers to which we don't actually know the answer. So here's one example of that. So every now and again in this list of primes, we see pairs of primes with a difference of just 2. So if you subtract one from the other, you get 2. So 19 and 17 is one such example. 71 and 73, 1481 and 1483. So these are called twin primes because they come in pairs. And so here's the question. So if we keep on writing the list of primes to larger and larger and larger numbers, will we eventually find the largest pair of twin primes, that is, the largest pair of primes that differ by just 2, or will we continue to find these red pairs of numbers forever as we look at larger and larger primes in the sequence. And this is a question that no one knows the answer to. And so it's incredibly simple to state, right? I can explain it to you here today, but to prove whether this is true or not is a really, really hard problem. So there's something very tricky about the primes, and so there are lots of mathematicians all around the world who study number theory, and in particular study the distribution of prime numbers. And mainly it's because mathematicians are just curious, right? We have this question, are there a finite number of twin primes or not? And we just want to know the answer, right? So, we want to know the answer to that question. So mathematicians want to study prime numbers. And often when mathematicians want to study some quantity, what they do is they sort of put all the information, all the stuff they want to study into a function. So it's just sort of a way of bundling up all the things we want to study into one object. And then mathematicians know what to do with functions, right? We know how to add them and multiply them and integrate them and differentiate them. And so it's a useful way to study something. So you can do the same thing with the primes. So there's a function which encodes all the information about the primes. So it's called the Riemann zeta function, named after the mathematician Bernhard Riemann, who lived about 150 years ago. And it's written as the Greek letter zeta. So this zeta is just a shorthand for this set of mathematical instructions, which are right here. And the thing to note is that this set of instructions contains the prime numbers. So here's a 2, 3, 5, and the ... just means I ran out of space, but there should be an expression like this for the prime 7, the prime 11, 13, and so forth, but I just ran out of space on the slide, and so couldn't write it down. Right, and this S here is just a placeholder. So we want to calculate, say we want to calculate the zeta function at 2, then we just replace everywhere we see an S, we replace with the number 2. And now we're calculating zeta of 2. So zeta of 2 is just a number, and this set of instructions here tell us how to calculate that number. So let's start doing this. So we take the expression that belongs to the prime 2, first of all. So we have 1 divided by 1 minus 1 over 2 squared. 2 squared is 2 times 2, which is 4. So we have 1 over 4, 1 quarter here. So 1 minus 1 quarter is 3 quarters. And if you remember your rules about what to do with fractions, if you have 1 over a fraction, then the rule is you just flip the fraction upside down. So we replace this first expression here by 4 over 3. So if that was too complicated or you didn't want to be bothered with doing the calculation, it's very easy to type that into a calculator or a computer and get it to work out the number for you, and it would give you exactly the same thing. It might perhaps write it as a decimal, but it's essentially the same thing. Okay, so we calculated the factor that went with the prime 2, and now we're going to do the same thing for the factor, the expression that goes with the prime 3. So here we have 1 divided by 1 minus 1 over 3 squared, that's 1 over 9, so we have 8 over 9 on the bottom, so that gives us 9/8. So now we tell our computer, okay, take the 9/8 and multiply it by the one we had before, and we get 1.5. And now I have a bit more space, so I've moved the expression with the prime 7 onto the slide. So we just want to continue this process. We have 1.5, and now we tell the computer, calculate this one and multiply it by that. And so we get this number, and now we continue on, multiply this number by this number, and then we do the expression that belongs to the prime 11. And you see that this number isn't changing very much now as we keep multiplying factors from the new primes. We're up to 1.6, and then if we do the prime 13, we get 1.61, so that hasn't changed very much. And then you get bored with this process after a while. So this is what happens if you multiply the expressions for the first 100 primes. And so this is the beginning of the primes we have left over. Of course, there are an infinite number of primes, right? So we could continue this process of multiplying forever. But we actually don't have to, because the real answer is here. So it's pi squared over 6, which is just a number, which I've written out here. And you can see that we're pretty close to getting the right number, even after doing just 100 primes. And if you wanted a few more decimal places correct, well, your computer could easily calculate the first 1,000 primes or the first 10,000 primes, or whatever you wanted to get as close as you liked to the real answer for zeta of 2. Okay, so this is the thing to remember, just that the zeta function is a set of mathematical instructions, but crucially, they encodes information about the primes. So information about the primes is encoded in this number here. So by studying the Riemann zeta function, we can study prime numbers as well. So we didn't have to put in 2 here. We didn't have to compute zeta of 2. We could have put in any other number. We could have put in 3, 4. It doesn't even have to be an integer. And in fact, we could have put in a complex number. So if you know what complex numbers are, then that's great. If you don't, all it means to put a complex number into the zeta function is that if we draw a picture of the zeta function, it looks like this. It looks like a surface. So if we draw a picture of the zeta function, we get a surface. It actually goes out to infinity. I don't know, it looks a bit like corrugated metal or something. And it goes off to infinity in every direction. And I've just taken a chunk out of it and drawn it on the board for you to look at. So what have we got here? Well, so we have zeta of x plus iy. So I is the square root of -1, imaginary number. And so what we've done is we've taken lots of different values for x lying between 0 and 1/2, and lots of different values of y lying between 100 and 120. And for every combination of x and y, we've calculated the zeta function in much the same way as we did on the previous slide. And then we've plotted the size of that zeta function as the height of the surface on this picture here. And so the x runs between 0 and 1/2, and y runs between 100 and 120. So, as I say, I've chopped a piece out of this infinite surface to show you, and I've been very selective about the piece that I've chopped out, because mathematicians believe that the only place, essentially the only place, where this purple surface touches down to the ground is along this line where I've chosen to slice through the surface. So along this line where x equals 1/2. And so this is kind of peculiar, right? Because say we took just a random surface. I scrumple up a piece of paper, and I put it down on the desk, and we ask, well, where does this paper, this kind of random crumply surface, where does it touch down to the desk? Well, it touches here and here and here and over there. And if we'd crumpled this paper and found that all the points where it touched the desk, or even almost all of them, lined up in a perfectly straight line. Say we'd done this with a huge piece of paper and we had hundreds and hundreds of points lining up in exactly a perfectly straight line, we think that was really weird, right? Because we'd expect it to touch the desk in lots of different kind of random places. So there's something very particular going on here with this Riemann zeta function if it's really true that it essentially only touches down to the ground on points along this perfectly straight line. So I said mathematicians believe that it's true that this is basically the only place the purple surface touches the ground. But in fact, no one is able to prove if this is true or not. And so this is one of the biggest unanswered questions in mathematics. And it's so big that it has a name. It's called the Riemann hypothesis, named after Riemann, who was the one who first suggested that this might be true. It's a really famous problem. There's a maths institute in the States that's offering $1 million to anyone who can prove this, who can say if it's true that this function only touches down to the ground at points on this line. And it's also made it into the popular media. So I think there are 4 popular science books on the Riemann hypothesis that have been published in the last 5 years. And it's also made it into the television series Numbers. So I don't know if you watch this series, but it's about a mathematician who goes around solving all the crime cases by using sophisticated mathematics. And there's an episode where there's a mathematician who claims to have solved the Riemann hypothesis, and then his child gets abducted because the kidnappers want the $1 million as their ransom money. So this is a major, major question in mathematics that mathematicians everywhere would love to solve, and not just for the $1 million, but because, as I said, mathematicians are curious, and we want to know the answer to this question. So lots of mathematicians work on the Riemann hypothesis and related problems, but it's a really, really hard problem, right? No one's managed to even get close yet. So there are other problems which are slightly easier and are like little steps on the way to the Riemann hypothesis. And it's one of those that I want to tell you about today. So one of these problems is, is the following question. So if we walk along this line here, and we watch the purple function as it bounces up and down in between the points where it touches down to 0, the question is, how fast, on average, does the height of this purple surface grow as I walk along this line? And this is the question that's related to the Riemann hypothesis. So what do we mean by that? What do we mean by how fast does a function grow? Well, so here's a linear function, right, a straight line. And here is another function. This is a quadratic, so this red curve. And so we can see that the red curve grows faster than the blue curve, because if we walk out along this x-axis here, and we look at the height of the blue curve at any point, then the red function gets up higher faster as we walk out this line than the blue function does. So the red function kind of gets steeper and really takes off, so it grows faster than the blue line. So now we want to look at the Riemann zeta function. So this is what you get if you take that purple surface and you slice through it along the line where it touches down to 0. So it's like looking at the leading edge of that the piece of purple surface that I was showing you before. So here it is, right? It hops along, it touches down to 0, then it bounces along. And it's not as easy to say how fast it's growing. It's not as easy as these two functions because it kind of bounces up and down. But you can see these peaks, they get larger as we go this way, right? And so somehow on average, this function is growing larger as we head out this way. And we want to answer the question, how fast on average does this function grow? So how fast on average does the height of this green curve grow as we move this way along that axis? So let's see, what do we do if we want to find the average height of a function? Well, so here's the function f of x equals x. And we want to find the average height, or the average size of f of x equals x between x is 0 and x is t. So that is, we want to find the average height of this red line here between 0 and the distance out here, t. So this red line is f of x equals x, or if you prefer, here's the y-axis and there's the x-axis, and it's the line y equals x. So it's a line that goes up at 45 degrees, so it's like a really steep hill. If you go out a distance t in this direction, then you've also gone up a distance t. Okay, so we want to find the average height of this line between 0 and t. So here are your options. So the answer is one of these. So hands up if you think the average height of the red line between here and here is t. Hands up. Who thinks it's t squared over 2? T over 2? Or t squared? Okay, so you've exactly illustrated my point, right? You almost all could tell that the answer was c, t over 2, and you probably just had to kind of think about it intuitively, and you didn't have to do any very complicated mathematics. So in this simple case, it's easy to see that you have a line that starts at 0 and ends at height t, and you want the average height. Well, it's a straight line, so the average height is going to be right smack in the middle, and that's going to be t over 2, or half t. Okay, so for this simple case, we could figure out what the average height was without having to do any complicated mathematics. But if we wanted to do it sort of strictly, rigorously mathematically, what we do is we integrate the function. So our function is f of x equals x, and we want to integrate it from 0 to t, and then we want to divide by t, which is the length of the interval that we're integrating over. So f of x is x. Integrate from 0 to t and divide by t. The integral of x from 0 to t is t squared over 2. And then we divide by t, so we cancel a t on the top and the bottom, and we get t over 2. Right? But you all knew that already before I did this calculation, because in this simple case, you don't actually need to integrate. So, if you've met integration, then that's fine. If you haven't met integration, then this symbol doesn't mean much to you. But it's the same with a lot of mathematics. So the symbols are just shorthand for a set of instructions that anyone with mathematical training would know how to follow. So it's maybe a bit like reading a map. So say someone had never seen a map before, and you gave them a map, and you said, you're here, and you have to get there. Right? They wouldn't know what to do, because they wouldn't know anything about scale, they wouldn't know how to orient the map, they wouldn't know what the little lines on the piece of paper meant. But if we've used maps, if we're familiar with maps, then a map is actually a very efficient way for one person to tell another person how to get from here to there, if they don't have a sat nav. So And it's the same with mathematical notation. So this symbol, which is called integration, tells a mathematician to carry out a specific set of instructions, and so anyone with the necessary mathematical training can follow out the same set of instructions, and it's a very neat shorthand. So to find the average value of a function, the average height of a function, what we need to do is integrate. So if we go back to the Riemann zeta function, then what we want to do is to integrate in exactly the same way the Riemann zeta function. So it turns out that actually we can get even more information about the average values of the zeta function if we calculate this with a 2, an exponent 2 up here, or with an exponent 4, and if we could also calculate it with 6 and 8 and 10 and so forth, then we'd really have all the information we could possibly want about how fast this function grows as it hops along in between its zeros. So what we really want to calculate is this quantity here with 2k, so some even number, right? K is 1, 2, 3, 4, 5, 6, and so forth. And if we could calculate that for all those values of k, then we would have the answer that we want. We'd really know how fast the Riemann zeta function grows. So this is what we need to calculate. And these quantities are called moments of the Riemann zeta function. So, well, how are we going to do this? Well, so first of all, let's see what's the connection with mathematical physics. So say we take this picture here of the Riemann zeta function. So this is, remember, if you slice through the purple surface and you're just looking at that leading edge as it hops along in between the points where it touches down to 0. So let's look at this picture, and let's just look at the points where it touches down to 0. So what if we go along and we mark off on this black line, on this axis, the points where it touches down to 0. So we put little red X's or something along this line every time the function touches down. And say we do this, and we do it until we've got 30 points marked off on our axis. And then we chop out that piece of line, and we wrap it around a circle, because it's easier to look at that way. And then we could do, so now we have a set of points on a circle, and then we could do the same thing. So this picture, of course, goes on and on and on forever. I've just drawn a piece of it here. But so say we now go further out along this picture, we find a place and mark off another 30 points on the axis, and we wrap them around a circle. And then we do the same thing again, another 30 points and wrap them around the circle. These then are pictures of the zeros of the Riemann zeta function. So the pictures of the points where the Riemann zeta function touches down to 0, and we've wrapped them around a circle for convenience. So you look at these points and you think, well, I don't know, that doesn't look like there's anything particularly special about them. Maybe they're just random points on a circle. So, so let's see. So what do random points on a circle look like? So this is the picture that you'd get if, so say you blindfold me and you give me a big piece of paper and you give me a pen, and I at random pick a point on a circle on that piece of paper. And then you spin me around several times, so I've completely forgotten where the first point was, and then I do it again. I pick another point on a circle. And you do this 30 times. You spin me around 30 times, and I pick 30 points at random on the circle. Then I might get something that looks like this picture here. And then if you did that again with a clean sheet of paper and you put 30 more random points on the circle, you might get something like this. And if you were really mean, because I'd be feeling dizzy by this time, and you did it again with a blank sheet of paper, then you might get a picture that looks like that. So these are 3 instances of 30 random points plotted on a circle. Okay, and you look at those and you think, well, actually they don't look at all like this, right? Because sometimes we have points that all land really close together. And sometimes we have spaces where there are big gaps between the points, and that it just doesn't seem to happen up here, right? These seem to be much more regularly spaced than the random points on a circle. Okay, so these points aren't random. So what are they? Well, let me show you some more points on a circle. So this top row, you look at those, and they seem to be distributed pretty much the same as the second row. So I think if I took one of the 6 top circles and I just showed it to you and said, does this come from the top row or does this come from the second row, I think you'd be really hard-pressed to tell me whether it was from this row or this row. Because really, by eye, the points look like they're distributed pretty much the same. Okay, so what are these things in the top row here? Well, these are eigenvalues of randomly generated 30 by 30 unitary matrices. Okay, so what does that mean? Well, a matrix, a 30 by 30 matrix, is just a 30 by 30 array of numbers. So here there are 900 numbers arranged in a 30 by 30 array. And a random matrix just means that you choose the numbers at random to stick into your array. So I've just chosen random integers, but you don't have to put integers in your matrices. You can put whatever you want, real numbers, complex numbers, whatever you feel like. So we have this array, this 30 by 30 matrix. And if someone gives you a 30 by 30 matrix, it turns out that you can calculate 30 special numbers called eigenvalues. And again, it's one of these things. If you've seen the procedure to do this, it's actually pretty simple. Simple enough that it's often taught in school. But obviously, if you've never seen it before, then you just have to take my word that if someone gives you a 30 by 30 matrix, you can calculate these 30 special numbers called eigenvalues. And then if you plot them on a circle, then you get pictures like these top row of circles here. OK, so for some mysterious reason, the zeros of the Riemann zeta function appear to be distributed like the eigenvalues of random matrices. So random matrix theory was developed in the 50s by physicists, in fact. So physicists were doing experiments in their labs, and they were experiments with the nuclei of atoms. So you know everything around us is made up of atoms, right? Me and you, the floor, the tables, whatever. And atoms have a nucleus, which is made up of protons and neutrons, and also some electrons. So the physicists would take the nucleus of the atoms, the protons and neutrons, and they'd take an extra neutron and fire it at the nucleus, and they'd get all jumbled up for a while and make a sort of compound particle which had a higher energy. And the physicists would measure that energy. And they do this over and over again. So they do the experiment lots and lots of times, and they get a picture that looks like this. So they did these for quite large atoms like thorium and uranium. And so here, energy is plotted along this axis. And they did the experiment many hundreds of times, and they've plotted how many times they got a certain energy. And you can see that there are certain energies, like this one here, where they measure that energy many, many, many times as they repeated this experiment. And similarly, this energy here, and then here. And so there are these very definite spikes, these energies that recur over and over again. And the physicists wanted to understand where these spikes occurred. So these are, like, you call them resonances or eigenvalues, if you like. They're very specific energies that kept appearing in these experiments. And the physicists wanted to predict where they occurred, but it's really hard to model these very complicated atoms in a very detailed way. But what they realized was that if you go along this energy axis and you mark off with an X the points at which these spikes occur, and you say you did 30 of them, and you wrap them around a circle, well, you get a picture that looked exactly like the picture of the eigenvalues of random matrices. So the physicists realized that they could do calculations with random matrices and get answers that would tell them about the distribution of these energy spikes that they were looking at. And so a whole theory of random matrices developed. It became an area in mathematics, in mathematical physics, in its own right, and obviously proved to be very useful in physics. So, but to get back to the Riemann zeta function, we looked at the picture of the Riemann zeros on the circle and the picture of the eigenvalues on the circle, and we could see that they looked as if they were very similar. But someone had to be the first person to realize that those are the things you should compare, right? Who would possibly think that you should be comparing the zeros of the Riemann zeta function with the eigenvalues of random matrices? It's obviously it's not obvious at all. So this is how it happened. So in 1972, these two men met. So Hugh Montgomery was a very young mathematician at the time, and he was studying the zeros of the Riemann zeta function. So he was studying how they were distributed on the circle, like as we just looked at. But being a mathematician, he had a formula, right? He didn't look at the pictures. He had a formula which described how those points, those 30 zeros, were distributed on the circle. And so he was at the Institute for Advanced Studies in Princeton. And I guess at the Institute, everyone gets together at a certain time of day to have tea in the common room. And at the Institute at the same time was a very eminent physicist, Freeman Dyson. And so Montgomery and Dyson got introduced. They were drinking their cups of tea, and someone introduced them. And what did they talk about? Well, what do scientists talk about when they get together? As I said, they're curious people, and they're always interested to hear about other kinds of science, even if there's no apparent reason why they, there's no specific reason why they'd be interested in it. But so Montgomery starts to tell Dyson about what he's been working on, right? He tells him about this formula which describes how the zeros of the Riemann zeta function lie on this circle. And Dyson looks at this formula, and he studies random matrices, and he says, that is exactly the same formula that you get to describe the distribution of eigenvalues of random matrices on a circle. And so that's where this whole field started. So completely by accident, just a coincidence that these two men were introduced over their cup of tea, and they talked about what they were working on and realized that they were looking at exactly the same thing in two completely different areas of mathematics. So, and Hugh Montgomery gave me a copy of this letter. So this is a letter that Freeman Dyson wrote, like April the 7th, 1972. He wrote to Atle Selberg, who was another mathematician at the Institute, and he says, the reference which Dr. Montgomery wants is, and he refers to the most famous book on random matrices, pointing out that Montgomery could find this exact same formula in that book, referring to the distribution of eigenvalues of random matrices. So this is how the whole field started. This is how people realized that there was this connection. So let's go back to our problem of trying to calculate the moments of the Riemann zeta function. So remember, what we wanted to calculate was this quantity here, and what we really want to know it when k is 1, when k is 2, 3, 4, 5, and so forth for all k's. So number theorists know a certain amount about this. So they know that it looks a bit like the expression over here. So ak is a product over prime numbers. They know it grows like log t to the k squared. But there's this part of the formula here, this blue fk, which is incredibly, incredibly hard to calculate. Right? So remember, we want this formula for all values of k. So we want to know the whole sequence of f numbers, f1, f2, f3, f4, f5, and then we'd really have a good handle on how fast this zeta function is growing as it hops along between its zeros. So the goal is to calculate these f numbers, but it's a really, really hard problem in number theory. So before random matrix theory, f1 and f2 were known. So f1 is 1, f2 is 1 over 12. So they're quite simple numbers, right? They're just fractions, but incredibly hard to calculate. So these were calculated almost 100 years ago. And then there's a guess for f3. So the guess for f3 is 1 over 8,640. Right? But beyond that, the number theorists really didn't have any idea of what f4, f5, f6 were. So they really didn't have any idea how to calculate those, because it's a really, really hard question in number theory. So, in 1996, there was a conference in Seattle. So it was a conference where all the famous mathematicians from around the world who were working on the Riemann hypothesis all got together to exchange ideas and to tell each other what they were working on, see if they could make some progress on the Riemann hypothesis. And so at this meeting, there was Peter Sarnak, who's a very famous mathematician who's working in this area. And also invited to this meeting was John Keating, who has a background in physics, in mathematical physics, and who's worked with random matrices. So even though this connection, the zeros on the circle look a lot like the eigenvalues on the circle, this connection had been known since the 70s, but no one had actually used it practically really to do calculations in number theory. But so John is thinking, maybe you can use random matrix theory to calculate something about the Riemann zeta function. And the number theorists are like, no way some physicist is going to come in and answer these 100-year-old questions with some strange technique from physics when we can't solve the problem ourselves. So Peter Sarnak says to John Keating, he says, look, if you really want us to listen to you, what you need to do is use random matrix theory to calculate F3. Right? So to calculate this number, which the number theorists conjecture is 1 divided by 8,640. Right? So Sarnak says, you go away and do that, and then we'll start to listen to you. Okay, so John went back to Bristol, where he was working, and he had a brand new graduate student, and that was me. And so we started together to work on this problem of trying to use random matrix theory to calculate these F numbers. And it turns out that you can do it. So here are the first few F numbers. So I've written them like this using this factorial notation because we can see a pattern this way. So factorial, this exclamation mark here, it just means you multiply together all the numbers lower than the one you started with. So 5 factorial is 5 times 4 times 3 times 2 times 1. So 0 factorial is 1, just by definition. So this is 1 over 1, which is just, which is exactly as the number theorists already knew. But I write it like this because of the pattern. So here's F2, 0 factorial over 2 factorial, 1 factorial over 3 factorial. So that's a 12th, which again agrees with the known value of F2. Here's F3, 0 over 3, 1 over 4, 2 over 5. And yes, indeed, that's equal to 1 over 8,640, which was the guess that the number theorists had. But you can go on and you can calculate any of the F numbers in the sequence because there's a pattern, right? If I asked you what F365 was, you'd be able to tell me because you'd work out what the pattern was, and it'd be a long expression, but you'd write it down and you'd be able to calculate any number in this sequence that you might want. So using random matrix theory, you can calculate this sequence of numbers. So it took us a couple of years to do this, to figure out really the right way to do it. And then by that time, sort of 1998, there was another conference on the Riemann hypothesis, this time in Vienna. So John Keating was invited to give a talk at this conference. So we go along there, and we meet Brian Conry, who's a number theorist. And so he's a number theorist. He was working in California. Now he also works part of the time in Bristol. So he'd met John at the previous Seattle conference. And so, we met in the corridor, and John and Brian are talking. And at some point, John asks Brian, I see you're giving a talk tomorrow. What is it that you're going to speak about? And Brian looks so proud. And he says, we've been working for years, and we finally managed to calculate F4. So I look at John, and I can see this little smile just starting to sneak into the corner of his mouth, and he is waiting, right? He is just waiting for Brian to ask him the same question. So John, what are you going to talk about tomorrow? And then John said, we've calculated all those F numbers. So there was a moment of tension there, right? Because it's never nice when you've been working on something for ages and ages, and someone else comes up and does exactly the same thing at the same time. So things could have gone badly wrong at this point, but luckily John and Brian are good guys, and they realized that what they had to do was check that we had the same number for F4. So, all of you know, if you've done some calculation one way, measuring up your living room for new carpet or something, and someone else does it in a different way, and you come up with the same answer, then you're pretty sure that you did it right. Yeah? And so we calculated F4 using random matrix theory, and Brian calculated F4 completely differently using just number theory. And so if the numbers agree, then we're all pretty confident that we did the calculation right, that we didn't make a mistake somewhere along the way. So we're in this institute in Vienna, and we go off and we find a room with a chalkboard, and so we write down our number for F4. So here it is, 0 over 4, 1 over 5, 2 over 6, 3 over 7. And then Brian writes down his number for F4, 24,024 over 16 factorial. And I don't know about you, but it's not entirely clear that these are the same number. So, you know what you have to do when you want to check if two fractions are equal. You have to get them over a common denominator, and you're allowed to cancel things off the top and off the bottom. Right, the same thing off the top and the bottom. So we go to work trying to check if this is the same number, but we're all really nervous, right? Because if these numbers don't agree, then one of us has made a mistake. And John and Brian have to give their talks the next day, and you really don't want to stand up in front of the world's best mathematicians and present a result that could possibly be wrong, right? So we're really nervous. The chalk was slipping out of our sweaty hands, and we're canceling 5s with 3s, and no, that's a mistake. I'll start again. But eventually we did manage to check that these are in fact the same number, and then everyone was happy, right? Because we had confirmation that we'd done the calculation right. And the next day, John and Brian could give their talks and show that we'd come up with the same number using two different ways. And that was really when number theorists started to believe that you could, in fact, use random matrix theory to answer important questions in number theory. So they began to have faith that this method would actually work. And so that was sort of about 10 years ago. And from then, we've gone on to find more and more ways in which you can use random matrix theory to attack really serious and old problems in number theory. So we've sort of gone on from strength to strength from there. Right, and it makes a good story because it's the physicists coming in and answering problems in number theory, sort of unusual combination of mathematics. And so it's an unusual enough story that it made it into the movie Proof. So this movie came out a few years ago, and it's about a mathematician. So in his day, he was like the most amazing mathematician, one of the greatest minds of his generation, and brilliant mathematician. And but eventually he gets old and he dies, and he leaves behind him a daughter who's also a mathematician, and also this study full of books and notebooks and scribblings, all the mathematical work he's done over the years. So the graduate student decides that he's going to go through the study and see if there's anything in all these mathematical scribblings that should be published after the mathematician's death. So he's going through the study, and he finds a notebook, and in this notebook is the most amazing proof. So in the movie, they don't actually tell you what it's a proof of, but it's some huge problem in number theory. So let's say it's the Riemann hypothesis. So he finds the proof in this notebook, and the only question is the work the father's, or is it the daughter's? So in the words of the graduate student in the movie, the proof is very hip, and it uses current mathematical techniques, including random matrix theory, and so presumably these are techniques that the father may not have been familiar with. So there you go, Hollywood's hippest mathematics. Thank you.
I think we know that prime numbers are sort of used in cryptography, and one of the things that makes code secure is the difficulty of factorizing large composite numbers. Would progress on the Riemann hypothesis have any impact on that problem?
Well, so progress on the Riemann hypothesis definitely tells you about the distribution of prime numbers. So it would, in some sense, have applications to understanding the distribution of primes, which would in turn have an impact on cryptography, as you say. I mean, it may not immediately help you factor large numbers, but they're all tied up. The questions are all tied up in the same sort of area.
These circles with the points around them. If you were to put those circles consecutively next to each other, creating a long tube, forever, would there be some number for the amount of points around the circle where some pattern emerged across the length of the tube, rather than it merely appearing slightly random?
So if you're talking about the random matrices, there'd probably be no pattern if you put many. You're talking about the Riemann zeros. So I mean, there are some long-range correlations between the Riemann zeros. So it's possible you might see something if you lined up your circles one after another.
I'm not sure it's quite fair to claim Freeman Dyson for theoretical physics, since his early papers were in number theory. So I think he's a classic example of somebody who's ranged across the whole sphere, and so is well placed to spot things like that. But thank you very much. It's lovely.
I wondered if you could go back a few slides to your graph, sort of the side-on view of the surface that you were talking about. That was the one. I was just looking. Is it just the way that it's been drawn, or does it actually seem to go below the axis there?
It's not a good picture. I mean, sometimes it doesn't quite touch the axis, and sometimes it goes below.
I just wondered if it went below. Is it supposed to go below at all?
It's not supposed to. No, it's just the way it's drawn.
This may be a bit unfair, but I hope you'll have a go. When you come to such a beautiful thing as your 0 factorial times 1 factorial times 2 factorial over 3 factorial, 4 factorial, 5 factorial, I mean, that must be as near bliss as it gets, mustn't it? Can you remember what it was like when you realized it had this wonderful form?
I mean, that's the wonder of doing mathematics, is that every now and then you come up with these amazingly beautiful formulae So, I mean, I don't know if I can remember what I felt like that exact moment, but I mean, in general, when you're doing mathematics, you work really hard for a long time and sort of feel like you're getting nowhere, and then you find this most amazing result, and it's like the best feeling in the world. So you're absolutely right. I mean, it's amazing when you get a result like that that's so clean and so neat.